So far in this class, we've been focused primarily on linear functions and linear relationships between two variables. And that's because the calculations involved with linear equations were relatively simple, and we were able to do most of those calculations by hand. We're now moving on to talk about nonlinear relationships. And for a lot of these calculations, we're going to rely a little bit more on technology because the algebra becomes a little bit awkward. But a lot of the things that we do in the nonlinear situation are the same as the ones that we do in the linear situation. So to introduce our first type of nonlinear function, let's start by looking at some input-output tables. So in this example, we have input representing years since 2000. This will be our X variable. And output representing price in dollars of some item. This will be our Y variable. And in this table, we see every time we go down a row, our input increases by 1. And examining the pattern in the outputs, we see that each time we go down a row, our output increases by 2. So when the change in X is plus 1, the change in Y is plus 2. And we see that these are linearly related data because the rate of change is constant. A constant change in X produces a constant change in Y. Every plus 1 in X produces a plus 2 in Y. And we can read the information to write down a linear equation off the table. We see that we have an increase in 2 of Y, an increase in 1 of X. So our slope is the change in Y over the change in X, or just 2. The intercept is the output when the input is 0. So our intercept is 1, which gives us the equation y equals our slope of 2 times x plus our intercept of 1. We can also go through the table and plot each pair. When x is 0, y is 1. When x is 1, y is 3. When x is 2, y is 5. When x is 3, y is 7. When x is 4, y is 9. When x is 5, y is 11. And we see that these points all lie along a straight line. We can draw a straight line that passes through all of those points. So we can draw a straight line that passes through all of those points, which is part of why we call this kind of relationship linear. Linear relationship, graph is a straight line, equation is linear. Let's contrast that to another data table. In this data table, again, we see each time we go down a row, our input increases by 1. But now, each time we go down a row, our output increases by different amounts. Right, from 1 to 2, that added 1. From 2 to 5, that didn't add 1 again, that added 3. From 5 to 10, we add 5. 10 to 17, we add 7. 17 to 26, we add 9. So what's going on? Every time we go down a row, the change in x, or I'm sorry, the change in the output is increasing by 2. So the change in x is constant, but the change in y is increasing. We don't have a constant change in y, but we see that the change in y is constant. And that's characteristic of this new pattern. This is not linear because the rate of change is not constant. And if we were to plot all of these points, when x is 0, y is 1, when x is 1, y is 2, when x is 2, y is 5, when x is 3, y is 10, when x is 4, y is 17, when x is 5, y is 26. We see that these do not line up along a straight line. Right, if we try to draw a straight line through any pair of these points, that line misses the other points. So this graph is not a straight line. We have a nonlinear relationship in the table. We have a graph that is not a straight line. And this is a new kind of pattern. This is the new kind of pattern that we're going to be discussing in this video. This pattern is what's called a quadratic pattern. The data in example 2 can be modeled with what's called a quadratic function. What's a quadratic function? A quadratic function is one whose equation can be put in the form a number times x squared plus another number times x plus a third number. And this first number, the number that's multiplied by x squared, can't be 0. So we have to have the x squared term. These two can be 0. So it might turn out that we don't have an x term. It might turn out that we don't have a constant term. To be quadratic, we have to have the x squared term. So just very briefly, we're going to go through and make sure that we can recognize these. This first example, we just have 3x squared plus 2x plus 3. This is quadratic, but it's not a function. Right, it has that ax squared plus bx plus c form, but it's not a function, just an expression. So this is not a quadratic function because it's not a function. Okay, so here we have f of x equals something. This is a function. And I have an x squared term. I have a constant term. Invisibly, I have a plus 0x. So this is a quadratic function because it has an x squared term, a constant term, and nothing else. On the other hand, notice this x to the power 1.2. In a quadratic function, we can have x to the second power, we can have just x, we can have constants. X to the 1.2 is not allowed. So this is not a quadratic function because quadratic functions can't have x to the 1.2, only x squared, x, and constant terms. Okay, so just like we can evaluate linear functions by just plugging in for x, we can do the same thing for quadratic functions. So if we have a quadratic function, f of x equals negative x squared plus 2x minus 1, we can take f of negative 3, right? F of whatever, we'll have negative whatever squared plus 2 times whatever minus 1. And in this case, our whatever is negative 3. Now, we could work out this arithmetic by hand, but this seems like a great job for the calculator. So I'm going to say negative parentheses, negative 3, close parentheses, to the second power, plus 2, parentheses, negative 3, minus 1. So I just punched in exactly what I have on the paper, and that works out to negative 16. Similarly, to take f of 2, right, f of whatever, I'll have negative whatever squared plus 2 times whatever minus 1. And in this case, the whatever that I'm plugging in is 2. So on the calculator again, negative 2 squared plus 2 times 2 minus 1 works out to negative 1. And notice that when I was entering this, I put my x value in parentheses. If we want to square a negative number, we need parentheses. Around it on the calculator. Right? If I say negative 3 in parentheses, square it. That means negative 3 times another negative 3, which works out to positive 9. But if I say negative 3 squared like this, right, that says take 3, square it, and then make the result negative. So if you are just always in the habit of putting the argument of a function in parentheses on your calculator, you'll never mess this up. Otherwise, remember, if you want to take a power of a negative number, that negative number has to be in parentheses. Okay, so let's think about what the graphs of these quadratic functions look like. So we have just a very simple quadratic function, f of x equals x squared. This is quadratic because it contains x squared and no other terms. If we wanted to write it in that form that we had for the generic quadratic, we would say f of x is 1x squared plus 0x plus 0. Right? If we want to think in terms of a, b, and c, a is 1, b is 0, c is 0. And let's think about what its graph looks like. If x is negative 3, then f of x is negative 3 squared, which we actually just worked out as positive 9. When x is negative 2, f of x is negative 2 squared. That's negative 2 times negative 2. That's positive 4. When x is negative 1, f of x is negative 1 squared. That's negative 1 times negative 1 is positive 1. When x is 0, f of x is 0 squared. That's 0 times 0 is 0. When x is 1, f of x is 1 squared. That's 1 times 1 is 1. When x is 2, f of x is 2 squared. That's 2 times 2 is 4. When x is 3, f of x is 3 squared. That's 3 times 3 is 9. So let's look at these points. When x is negative 3, y is 9. When x is negative 2, y is 4. When x is negative 1, y is 1. When x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 4. When x is 3, y is 9. Oh, okay. So if we want to, we can go and fill in kind of a smooth curve connecting these dots. And that curve looks something like this. This is a specific shape. It's called a parabola. And there are a couple of features of this graph I want to call your attention to. One is that it's flat at the bottom. So that point where it turns around, it's flat. It's not pointed. And the other thing I want to call your attention to is at the top. At the top, it's almost straight. So it doesn't curve back in on itself. It doesn't curve out faster. Right? If you draw it growing off, if you draw it going off the graph in basically straight lines, it'll look about right. So this shape is called a parabola. A parabola is either a U-shaped curve, like the one we just drew, or an N-shaped curve that's upside down. So I would call this shape U-shaped, and this shape N-shaped. It either opens up or opens down. Now, every parabola is a U-shaped curve. Not every U-shaped curve is a parabola. There are curves that are like flatter at the bottom or less flat at the bottom that are not parabolas. For this class, every U-shaped or N-shaped curve that we see will be a parabola, but you should be aware that it's possible that that doesn't happen. There's a special point on the parabola called the vertex. And the vertex is that highest or lowest point where the graph turns from going down to up or from up to down. If the parabola opens up, which happens when the x squared term is positive, then the y value of the vertex is the maximum value of the function. If the parabola opens down, which happens when that x squared term is negative, no, I misspoke. If the parabola opens up, right, then the vertex is at the bottom. And so the y value is the minimum value of the function. If the parabola opens down, so the x squared term is negative, then the y value of the vertex is the maximum. The vertical line that passes through the vertex is called the axis of symmetry. And what that means is if we pick up the parabola and we flip it across the axis of symmetry, it looks the same. The parabola is symmetric across that vertical line. The left and right sides are mirror images of each other. So let's take a look at a parabola and let's see what we can say about its shape. So this is the graph of some quadratic function. We know it's a quadratic function because the graph is a parabola. And before that, we have to observe that it's a function. And we know that it's a function because it passes the vertical line test. Any vertical line that we can draw across it only crosses the graph once. So we know it's a function because it passes the vertical line test. We know it's a quadratic function because it's specifically parabola shaped. If we want to find f of 4, we need to find the point on the graph where the x coordinate is 4. So that'll be this point. Looking across to the y-axis, we see that this is the point 4, 3. And so f of 4 is 3. To find f of 2, we want to find the point on the graph where the x coordinate is 2. That'll be this point. we see that this is the point 2, 5. And so f of 2 is 5. If we want to say, what is the number such that f of x is -3? Well, this is interesting, right? So here's the -3 on the y-axis. We have 2 points on this graph whose y-coordinate is -3. All right, we have the point -2, -3, and we also have the point 6, -3. So there are 2 inputs that give the output -3. F of -2 is -3, and f of 6 is -3. Now, that's something that we did not see with linear functions. With linear functions, right, each input only gives one output because it's a function. But with linear functions, it's also true that each output only came from one input. That's different with quadratic functions. With quadratic functions in general, each output comes from 2 different inputs. And that's okay. That's a thing that can happen with functions. But we have to be cautious. If we're looking for the input that gives a certain output, we expect to get 2. Okay, now we're asked for the y-intercept. That's where the graph crosses the y-axis. This is the y-intercept. And this is the point 0, 3. Our y-intercept is 0, 3. We're also asked for the x-intercept. And looking at this graph, we see that there are actually 2 x-intercepts. Right? Those are the inputs that give the output 0. We also see that we can't exactly read the coordinates of those points off the graph. Right? We see that the first one is between x equals 1 and x equals 2. I'm sorry, x equals -1 and x equals -2. That's this point. And then the next one is between x equals 5 and x equals 6. So we can't exactly read the coordinates of those points off the graph, but we can see where they are. Okay. And finally, the vertex. So this parabola opens downward. The vertex is this top point. The vertex is this top point, 2, 5. And we don't need to read the coordinates of that point because we already read them earlier for an earlier question. The vertex is at 2, 5. Okay, so that's a quadratic function represented in a graph. Let's take a look at a quadratic function represented in a table, and we can do all those same things. So here we have a table of x values and f of x values, right? Input values and output values. And we can tell that this represents a function because each input only appears once. How can we tell it's quadratic? Well, we can certainly see in this table that each time we go down a row, the input increases by 1. So the pattern we're looking for in the output is not a constant change, but a constant change in the change. So we decrease by 10, decrease by 6, decrease by 2, increase by 2, increase by 6, increase by 10, increase by 14. In the positive numbers here, it's easy to spot that our changes are increasing by 4. And we hope that we have the same pattern in the negative numbers. If you're not sure, you can use your calculator to double check, right? Negative 10 plus 4 gives us negative 6. Plus another 4 does give us negative 2. Plus another 4 does give us positive 2. So we know that this is a quadratic function because we see the change in the change is constant. When we want to take f of 4 or f of 2, we're looking for input 4 gives us output 3. So f of 4 is 3. Input 2, it happens also gives us output 3. So f of 2 is 3. When we want to say f of what gives us 19, we want to go the other way around. So output 19, we find twice, right here and here. Output 19 comes from input 0 or from input 6. If we were to graph this, the y-intercept would be the point with x-coordinate 0. So we can see that the y-intercept is in this row of our table. Our y-intercept is 0, 19. And then the vertex, well, the vertex is going to be the minimum or maximum output. And we see that happening in this row of our table. Our vertex is at 3, 1. And our quadratic pattern is unique among the functions we'll see in this course, in that when we have a quadratic function, the outputs either decrease and then increase again, or increase and then decrease again. Unique among the functions that we're going to study in this class, quadratic functions have a turning point, which happens at the vertex. So quadratic functions will either have a minimum value or a maximum value. All of the other functions we're going to see in this course, the linear functions we've seen already, and the exponential and logarithmic functions we're going to see in the future, those are either always increasing or always decreasing. Okay, so we've looked at graphs and tables. Let's see how we can actually work with a quadratic function from its equation. And when we work with the equations of quadratic functions, we're going to make significant use of technology. When we work with linear functions, we could go from a table to an equation by hand, right? We could find the slope and the intercept based on the table, or we could find the slope and just use any 2 points. There are ways to go from table to equation by hand, but the math is a little bit more intensive. So when we want to go from a table to equation by hand, for our purposes in this course, we're going to use technology. So first we're going to identify that this table represents a linear function. We see each time we go down a row, the change in x is constant. The change in y, well, for this I actually need to work out subtraction, right? So 180 minus 95. So first row, we're adding 85. 255 minus 180. Okay, then we're adding 75. 320 minus 255. Okay, now we're adding 65. 375 minus 320. Okay, now we're adding 55. Okay, we see that each time the amount we add goes down by 10. So we see that the change in the change in y is constant. So this is a quadratic relationship. Now we're going to use the calculator to find out exactly what equation we can use to describe that relationship. And in the last section, we saw that when we have a linear relationship, we can put the table into the calculator and we can use linear regression, to come up with the equation. To get a quadratic equation, we're going to again put the table into the calculator. So our x values in list 1, 1, 2, 3, 4, 5. Our y values in list 2, 95, 180, 255, 320, 375. And then we're going to say stat calc. To get something linear, we use linreg. To get something quadratic, we're going to use option 5, quadreg. So quad stands for quadratic here. Our x values are in L1, our y values are in L2, and I'm going to store my equation. So vars, right arrow to get y vars, function y1, and calculate. And this gives me my quadratic equation. So notice this is telling me the form ax squared plus bx plus c. So my a is negative 5. I'll have y equals, my a is negative 5, so negative 5 x squared plus my b is 100, so 100x, and then my c is 0 plus 0. And of course, adding 0 doesn't do anything, so we can skip plus 0. I will usually write down the +0 when I first write down the equation, just so I know I didn't like just forget about it. But then later on when I'm using the equation, I'll stop writing that down. So these values, let's go back and see what the story was about. We're told the law of supply and demand states that when the price of an item is increased, the number of items sold will decrease, so that the company's revenue is not a linear function of the price they charge. And we discovered it turns out it's quadratic. The table shows a company's revenue in thousands of dollars for various prices in dollars. So X represents the price in dollars, Y represents the price in thousands of dollars. So the question, how much revenue, is asking us what is Y if the price is $3.75. So X is $3.75. So we want to take our equation and plug in X is $3.75. So we'll say -5 times 3.75 squared plus 100 times 3.75. And we get some awful decimal. I'm going to round it to a couple decimal places. Notice we're not talking about dollars, we're talking about thousands of dollars. So we could carry more than 2 decimal places, but for the sake of fitting in the blank, right, I'll write down the exact value here. 304.6875. I'm going to just round it to 1 decimal place for the sake of fitting in the blank. 304.7 thousand. If they price the item at $3.75, they expect a revenue of $304.7 thousand. Okay, so we know how to answer the kinds of questions where we're given the value of X and we're asked to find the value of Y. We're given the input, asked to find the output. There are 2 other kinds of questions we can ask. We can ask questions where we're given the value of Y and asked to find the value of X. Right? We also had this for linear. Right? For linear functions, we could also ask questions where we wanted to find a value of X given a value of Y. But now we have something new. We might want to find the maximum or minimum value of a function. This is new for quadratics. Because quadratic functions, uniquely among the functions we'll study in this course, have that turning point, a maximum or a minimum. Right? This happens at the vertex. Now, when we had linear functions, finding x given y required that we do some algebra, right? It required more than just plugging in. The same is true for quadratics. And because the algebra involved in quadratics is a little bit more complex, we're going to use technology. There are 2 ways we can use technology to find y given x. The first way that we can do it is to use a table of values generated from our function. And we could generate a table of values by hand, but it's much easier to have the calculator do all the hard work for us. We're going to generate a table of values for the equation that we found in example 8. Right, so we had the equation y equals negative 5x squared plus 100. Here we have just the general instructions for creating a table of values to refer back to, but we're going to work through it together in this example. So first we go to y equals, and we already stored that equation. I'm going to delete the plus 0. We have the equation negative 5x squared plus 100x, y equals negative 5x squared plus 100x, already entered on the calculator. And this gives us the company's revenue from an item in thousands of dollars as a function of the price they set in dollars. And now we're going to use a table to find the price. So what is X? To get a revenue of 480,000. So this is telling us Y equals 480. This is telling us the value of X, or of Y, and asking for a value of X. To answer this, we need to solve the equation. Plug in 480 for Y. That equals negative 5x squared plus 100. So we're looking for the input that gives an output of 480. We've entered our equation. Second, we press second window on the calculator. So the second key in blue, followed by the window key along the top, to set up our table. We're only interested in positive values of X because, right, if I'm a company, I'm not going to set a negative price. I'm not going to pay you to take this thing away. I'm certainly not going to make $480,000 if I do that. So I'm going to set my table to start at 0. And then this triangle table or delta table set at 1 means my X values will count up by 1. Independent and dependent are set to auto, just means that the calculator is going to automatically come up with numbers for us. So now I press second graph to get the table. My X values start at 0 and count up by 1. My Y values, well, they're the output of the function. So depending on the exact model of your calculator, you might see what we see in the screenshot, where the largest Y value we currently see is 420. Or you might see what we see on the big calculator, where we see more X values and the largest Y value we see is 500. But I'm going to fill this in based on the screenshots, where the largest Y value we see is 420. And the values increase as we go downward. And so we'll scroll down. And when we scroll down on the smaller screen, or just as we look at the larger screen, we see that when X is 8, Y is 480. And so X equals 8 is a solution. But wait, there's more. We expect this function to increase for a while and then decrease. So we expect that Y will pass 480 and then come back again. So let's keep scrolling. And now I need to scroll on the big calculator also. Oh, it looks like y went up to 500 and then turned around. And it came back, and y is 480 again when x is 12. So we have a second solution. When x is 12, y is 480. So x equals 12 is a second solution to this equation. How can we interpret these solutions? To get revenue, of $480,000, the company should price the item at $8 or at $12. Either price will get revenue of $480. Now, this method works great when it works. It has the advantage of being relatively easy, right? We just make a table and then we look at it. Unfortunately, it doesn't always work. To see why, let's look at this table again. And suppose we wanted to find the price to get revenue of $350,000. Well, we see that when x is 4, y is 320. When x is 5, y is 375. 350 falls between there. As we keep scrolling, we see that y comes back down to 375 and then skips to 320 again. So in the table we're looking at, we don't see any rows where y equals 350. We suspect, right, we expect that this is somehow smooth. So we expect a solution between, so 15 and 16, and one between, what was the other pair of numbers? So 4 gives 320, y gives 370, or 5 gives 375, and a solution between uh, 4 and 5. When we have a problem that involves a quadratic function, or an equation that came from a quadratic function, we in general expect two solutions. Sometimes something weird happens. We're looking right at the vertex and we only get one solution. And sometimes we don't get any solutions at all. But the normal thing that we expect is to get two solutions. Okay, so the table will not tell us what those two solutions for y equals 350 are. We know there's one between 4 and 5 and one between 15 and 16. We don't know what they are. We can instead use a graph on the calculator combined with the intersect function. How do we do that? So we have the step-by-step instructions here, but we're going to do this for the example. So we're still working with the equation. No, we're going to go through the step-by-step instructions. So here we're just going to look at the screenshots, and then we'll do another example where we do all of the entry on the calculator. So we're solving an equation in the form f of x equals some number. In this case, negative 5x squared plus 100 equals 350. We start by pressing y equals, enter our left-hand side for y1, our right-hand side for y2. And then we're going to make a guess for the range of x values that contains our solution. A table of values can help. Here we're going to use the guess x is between 0 and 20. So we press window, enter our maximum and minimum x values, and then we use the command zoom fit to fit those x values. What zoom fit does is it says, I picked the x values I want. Now give me the y values that go with that. And we see in our graph the parabola, that's the graph of our quadratic function, and a horizontal line, that's the graph of y equals 350. And what we see is that these two graphs intersect in two places. If we don't see that, we'll go back to step 2 where we entered our guess, and we'll adjust our guess. Now we want to get the calculator to tell us the coordinates of those 2 points. We'll press second trace to get the calculate menu and choose the intersect function. The intersect function gives us 3 prompts: first curve, second curve, and guess. For first curve, we want to select our quadratic. For second curve, we want to select our horizontal line. And for our guess, we want to go close to the first point of intersection. If our curves only intersect once, our guess doesn't really matter. But if our curves intersect twice, we want to put our guess close to the point of intersection that we want. And when we press enter after choosing our guess, the calculator will say intersection, and then it'll give us an x value and a y value. In this screenshot, we see the point of intersection. X is about 4.52. And that value is a solution to negative 5x squared plus 100x equals 350. To find the other solution, we go back and select the intersect function again, pick the first curve, our quadratic, the second, our straight line, but now we put our guess close to the second point of intersection. And we see about 15.48 is a solution to negative 5x squared plus 100x equals 350. Okay, so this was in screenshots. Let's see another example where we go through the process together. In example 8, we found the equation negative 5x squared plus 100x describes the relationship between y, a company's revenue, and x, the price they set for an item. So we want to find out what price should the company set. So this is saying find x to earn a revenue of $450,000. This is y is 450. So we need to solve the equation. Negative 5x squared plus 100x equals 450. So on the calculator, we'll enter negative 5x squared plus 100x as y1, and we'll enter 450 as y2. We've already got our quadratic entered in y1. We'll enter 450 in y2. Then we'll press window. And I'm going to guess that x values between 0 and 20 will work. So I'm going to enter 0 for my x min, 20 for my x max, and I'm going to leave the rest of these numbers alone. Y is going to take care of itself when I go to zoom and scroll down to choose option 0, zoom fit. Again, that says, I gave you the x values I want. Give me the y values that go with it. So we see our quadratic function, that's the parabola, and we see a horizontal line, that's y equals 450. And to find the point of intersection, we say second trace, choose the intersect function. First curve defaults to the parabola, so we hit enter. Second curve defaults to the horizontal line, so we hit enter. Guess, we're going to find the point on the left first. So we move the cursor close to that, just using the left arrow. Hit enter. And we see the first solution to our equation, negative 5x squared plus 100x. The first solution to our equation is about 6.84. And then to find the second point of intersection, we do the whole thing again. Second trace, select intersect. First curve defaults to the parabola. Second curve defaults to the horizontal line. To get our guess, we move close to the second point of intersection and hit enter. To 2 decimal places, we have 13.16. And of course, the reason I kept 2 decimal places for each of those is that we're interpreting these as prices. To get revenue, of $450,000, the company can set prices of $684 or $13.16. Now, let's see a special feature that quadratics have. We cannot find a price that the company can set to make a revenue of $700,000. Right, so find a price. Again, that's asking us for X. And it's giving us Y. In order to find such a price, we would need to solve negative 5x squared plus 100x equals 700. Going back into my y equals, I'm leaving negative 5x squared plus 100x. as y1, but now I'm going to make my y2 be 700. And I'm going to leave my guesses, so I'm not going to go back to the window screen. I'm just going to say zoom fit again. And what we see here is that our horizontal line is just along the top of the screen. Right, that isn't super obvious in the screenshot. And so what's happening here is, so my parabola comes up and comes back down again, but it never gets up to 700. There's no solution because 700 is more than the maximum value of the function. So because 700 is more than the maximum value of this function, right, the maximum revenue is less than 700, the revenue never gets up to 700. So I suppose we might want to ask then, what is the maximum revenue? That's certainly a question we would ask if we were this company, right? Where should I price my item to make the most money? Well, depending on which way our parabola opens, finding the vertex will either tell us a maximum or a minimum value of y. Right? If our parabola opens downward, then this point at the top is a maximum. If our parabola opens upward, then this point at the bottom is a minimum. We'll only ever have one or the other for a particular quadratic function, and we'll only ask you for the one that exists. So how can we find the vertex? We have a way to do it by hand, and we have a way to do it on the calculator. To do it by hand, we have a formula for the vertex. And the way that this formula works is it gives us a formula for the x-coordinate, and then to find the y-coordinate, we evaluate the function at that point. The x value of the vertex is negative b over 2a, and to find the y value, we evaluate the function. So here's how this works for our revenue function that we've been working with. So the graph of this function, we've looked at it a few times. The graph of this function is a parabola that opens down. And we know that that's going to happen partially because we've looked at the graph. We also know that because the x squared term is negative. So even if we hadn't looked at the graph, we would know that this is a parabola that opens down, which means that it has a maximum. And that maximum occurs at the vertex. So we can ask the question, what is the maximum revenue that the company can make for this item? To answer this question, we find the vertex. And I'm going to use the vertex formula. My x-coordinate is, well, let's look at my function again. Right, I have f of x is negative 5x squared plus 100x. And I'm going to fill in the plus 0 because that makes it easier to see that in the form for the vertex, or for the standard quadratic, we have a is negative 5, b is 100, c is 0. So that a, b, and c are what goes into the vertex formula. So my x-coordinate is the opposite of 100 over 2 times negative 5. So I'm going to just put that into my calculator as the opposite of 100 divided by 2 times negative 5. And I get that that's 10. So for my vertex, the x-coordinate is 10. The y-coordinate, I'll take f of 10 is negative 5 times 10 squared plus 100 times 10. Negative 5 times 10 squared plus 100 times 10. We get 500. So the vertex is at x is 100, or x is 10, y is 500, which we can interpret in the context of this problem by saying that the maximum revenue is $500,000. And we get that maximum revenue if we set the price to be $10. Right? Y represents the revenue in thousands of dollars. X represents the price in dollars. Okay, so that method works great if we have relatively nice numbers. Right? Plugging into the vertex formula works great if the numbers are relatively nice. If we have unpleasant numbers, we can instead use the calculator to find the vertex. So how do we do that? So here we have an example of a quadratic function. 0.031x squared minus 15.3x plus 219.8. Those numbers are pretty unpleasant. We know that this function has a minimum because the x squared term is positive. So to find the vertex, we'll find a minimum. How can we do that? Well, we're going to start by graphing this function. So my y1, I'm going to say 0.0, I'm going to copy my function exactly, 0.031x squared minus 15.3x plus 219.8. Next, I'm going to go to Window and guess a range that my vertex might be in. My first guess is going to be 0 to 600, I expect kind of a big number because my value of a is very, very small. So I'm going to set my x values to go from 0 to 600, choose zoom fit to set the y values. And looking at the screen, I observe that the vertex is visible. Since the vertex is visible, I can now go to the next step. And I'm going to use that calc menu again. So second trace. But now I'm not looking for where two curves intersect. I'm looking for the vertex. I have a minimum command and a maximum command. I need to remember that my vertex in this case is a minimum, so I'm going to choose the minimum command. Okay. So in our example, we selected minimum because our graph has a minimum. It's a parabola that opens upward. And now let's look at the prompts here. So at the top of the screen, we see just what function we're graphing. And at the bottom of the screen, we see we're being prompted for a left bound. We want to put that anywhere to the left of the vertex. So now we're to the left of the vertex. We hit enter. And notice it put a little left bound marker. Now for the right bound, we want to go anywhere to the right of the vertex. This is fine. For our guess, we want to go somewhere close to the vertex. This looks fine. And then it tells us the coordinates of the minimum. So in our example, the minimum value of the function, that's the y coordinate, is about negative 1668.023, and it occurs at about x equals 246.77416. And I'm just recording all of the decimal places that I'm shown right now because this was just kind of a naked function. It didn't tell me what this function represents, so I don't know anything about what sort of rounding makes sense. So the calculator can find the coordinates of the vertex. We have to know whether it's a maximum or a minimum, and we have to get it on screen. Should you use the calculator or the vertex formula? Whichever seems easiest for a particular problem. Now, just like we could have approximately linear functions, we can have approximately quadratic functions. Just like we could make a line of best fit for an approximately linear relationship, we can make a quadratic curve of best fit for an approximately quadratic relationship. For the moment, the reason that you know that you want to choose a quadratic is that we're in a section called quadratic functions. We will talk about how to decide the best kind of function to use for a particular situation a little bit later on in this unit. How do we find the quadratic curve of best fit? Well, we use the calculator again. So here we have a data table about bottled water consumption since 1990. To fit a curve to it, I'm going to start by entering the data table on the calculator. So my x values represent the number of years since 1990, and my y values represent the bottled water consumption in that year. So 1990, that was 0, 95, 2000, 2005, 2010, and that's where our data ends. In 1990, 2.2 billion gallons of bottled water were consumed. In 95, we had 3.1 billion gallons. In 2000, we had 4.7 billion gallons. In 2005, we had 7.5 billion. And in 2010, we had 11.4 billion. Okay, so we've entered our x values. And now I'm going to say stat calc quadreg. My x values are in L1, my y values are in L2. I'm going to store my equation. So vars, right arrow, and just enter twice to select y1. Store my regression function in y1. And that gives me my a, b, and c values. If I want to check that this is a good fit, I'm going to say second y equals, turn on a scatter plot for these data, and then I'm going to say zoom stat to look at my graph along with my scatter plot and notice that my curve is a good fit. So let's go back and grab that quadratic function again. Stat calc quadreg. Of course, whenever we have one of these curves of best fit, our coefficients are going to be kind of unpleasant numbers. We're going to round them to 3 decimal places. So my a value is 0.021 when I round to 3 decimal places. My b value is 0.045. And my c value is 2.249. So to predict the bottled water consumption in 2014, we have x is 2014 minus 1990 is 24. So y is 0.021 times 24 squared plus 0.045 times 24 plus 2.249. We can just enter that on the calculator. So we get 15.425. Or we could use our stored equation. Right? We stored the equation in y1. The calculator understands function notation. So we could instead take y1 of 24 by saying vars, y vars, selecting y1. And that gives us 15.1674, etc. Again, The homework is set up to accept either one of these. They're slightly different because y1 contains the unrounded equation. Either way, I'm going to use the first one in my interpretation. You can pick whichever one you like better. In 2014, 15.425 billion gallons of bottled water were consumed. Okay. We can also ask a question, use our equation again, to predict in what year bottled water consumption will reach 20 billion gallons per year. To answer this, we need to solve our quadratic. Equals 20. And definitely I want to use the calculator for this. We'll use the intersect feature on the calculator for this. So I already stored my equation. I'll say 20 for y2. Right, so y1 is my equation that I stored when I did the quadratic regression. Y2 is just the number I want it to equal. Okay, so let's look back at our data set. The largest y value in our data set was 11.4, corresponding to x equals 20. So we want to go out past x equals 20 for the y value to get up higher. We might guess we'll get there sometime before x equals 30. So when I go to my window, I'm going to leave x min alone. I'm going to say, let's have x max go up to 30. And then I set my x values. I want the calculator to automatically set my y values, so I'm selecting zoom fit. And there I see my scatter plot, my curve going through it, and then my horizontal line. Now, I only see those intersecting once, but it looks like my other point of intersection is going to be at some negative x value. And I don't care about negative x values for this application. Right? I don't think that this trend is going to continue going backward in time before 1990. So I'm really only interested in this positive point of intersection. So I'm only going to find this one. So second calc, intersect, first curve, second curve, and then I'm going to put my guess close to this point of intersection that I can see. And I get x is 28.312, etc. So this is between x is 28 and x is 29. So let's look at the bottled water consumption for x is 28 and x is 29. There are a couple ways I could do this. I think I'm just going to look at a table. Right, I'm looking at y1 in my table. for x is 28 and x is 29. So for x is 28, my bottled water consumption is about 19.6 billion, and it's about 20.8 billion for x is 29. The question asks me, what's the first year that I'll have bottled water consumption of at least 20 billion? And that's x equals 29. So that's the year 1990 plus 29 is 2019. Bottled water consumption reaches 20 billion gallons per year in 2019. Right? The reason I needed a whole number is that like the year 2018.31 is not a thing, right? We only talk about whole number years. Okay, let's see one more example of an approximately quadratic relationship. So this is another application of that supply and demand thing that we talked about earlier. This company predicts that its profit from the sale of a certain item will be a quadratic function of the price they set for that item. But it's not as simple as the information we were given earlier. So they need to figure out what their profit will actually be. They do some focus group testing, and they find out that depending on the price, they'll make these profits. So if they price the item at $10, they'll make a profit of $57 million. If they price the item at $50, they'll make a profit of $73.6 million, and so on. So we need to convince ourselves that something quadratic is going to be appropriate here, even though we know it will because it says quadratic at the top of the lecture guide. We'll go to Stat, Edit. We'll enter our data, x in L1, y in L2. So our x values are 10, 20, 30, 40, 50, 60. Our y values are 57.0, 86.2, 99.4, 86.2 again, 73.6, and 53.2. So we'll say second stat plot, make sure that's turned on. I'm also going to go into y equals and clear out the stuff from the last problem so I don't have a bunch of weird graphs. And now I'm going to say zoom stat to see my scatter plot. Okay, and the big thing we notice in this scatter plot is it's, vaguely parabola shaped. In particular, our y value increases and then decreases again. If we get a parabola of best fit, it's going to be a parabola that opens down. Because it looks like our scatter plot has a maximum value. This is a good reality check, just so we'll notice if something weird is happening. Okay, so let's come up with our parabola of best fit. So I'm going to go to Stat again, Calc. I'm going to choose Quad Reg because I want a quadratic. My x values are in L1, my y values are in L2. I'm going to store the equation to y1 and calculate. I'm going to round my coefficients to 3 decimal places. We'll have y is negative 0.063 x squared plus 4.19x plus 24.4. So it happened that I didn't have to round B and C. Okay, now that we have our quadratic function, we can do all of the parabola stuff with it. We should probably look at the graph and make sure that it's a decent fit, right? I'm just going to hit graph here. That seems like a decent fit. We expect that the maximum profit will occur at the vertex. And we're going to use the maximum function on our calculator to find it. And we can keep our zoom stat window because the vertex is on screen right now, right? When we drew that graph, we could see the vertex. We see where the parabola turns from increasing to decreasing, so we don't need to monkey with our window. To find the vertex, we'll say second trace. For this parabola, our vertex is a maximum, so we'll choose the maximum command. Left bound, we want to be clearly to the left of the vertex. Right bound, we want to be clearly to the right of the vertex. And then guess we'll put somewhere in the middle. And we see that this function has a maximum. To find the maximum profit, we'll look at the y coordinate, which is about $94.38 million. To find the profit, to find the price we use the x coordinate. And we see that to make that maximum profit, we should set the price at about $33.41. Now, we could, instead of using the maximum function on the calculator, we could instead use the vertex formula with our rounded equation that we wrote down in part C. In part C, we wrote down that y equals negative 0.063x squared plus 4.19x plus 24.4. So for purposes of the vertex formula, we'll have A is negative 0.063, B is 4.19, and C is 24.4. And so the x-coordinate of our vertex is going to be negative 4.19 over 2 times negative 0.063. So negative 4.19 divided by 2 times negative 0.063. We get x is about 33.25. And then y is negative 0.063 times 33.25 squared plus 4.19 times 33.25 plus 24.4. which is about 94.07. This gives a maximum profit of $94.07 million, obtained with the price of $33.25. And notice this is a little bit different from what we got using the maximum function. They're about the same, right? If some analyst tells you to set the price at 33.41 versus 33.25, you're going to set the price at like 32.99 as a marketing person, right? So there's no substantial difference here. But the one we find with the maximum function is a little bit more accurate because we didn't use rounded numbers. We only rounded at the very end. So when you use the stored equation on the calculator, you get a little bit more accuracy, but you should get very similar results. And again, the homework is set up to accept either one. I generally prefer to use stuff that's stored on the calculator because that means I don't have to do a bunch of copying. However, I do need to remember all of the commands on the calculator. So if you prefer to use your rounded equations and to just handle the copying, that's also fine.